Hi there. Thanks for joining us again. This is Space Nuts, where we talk astronomy and space science. My name is Andrew Dunkley. Thanks for your company. Coming up today, we have some sad news about a company that was developing what would probably have been one of the great leaps forward in rocket science. Unfortunately, it's gone the other way, and we'll explain why. The UK's oldest satellite, which was launched not long after Neil Armstrong set foot on the moon, has done something weird. We don't know who did it. We don't know why. And wait till you hear the name of this thing. It'll make you laugh. And citizen scientists have proved their worth again by explaining why Magenta Aurorae appeared over Japan earlier this year. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's back again for more gruelment. It is Fred Watson, astronomer at large. Professor Fred, hello.
You're on a roll today, Andrew, with inventing new words. I love gruelment.
Gruelment. I'm going to write that one down too.
I'll write this one down too.
As when we were recording the TikTok, I had a slip of the tongue and I created a word called webspite.
Yes, webspite. It's when you use the World Wide Web to get back at somebody.
Yeah. What did I just say? Gruelment. Yeah, I'm going to write that.
Yes, which is, I can't read my own writing, so you'll have to tell me what that was.
Gruelment.
No, thank you, Andrew. It's a pleasure to be here, and you don't mind being grueled from time to time, as long as it doesn't get too often.
No, it's usually once a week with our Q&A edition, so... All right. We've got a lot to talk about. And first up is some very sad news about a company that they've been operating for quite some time. And they've been trying to perfect a system that enables you to get into orbit without having to actually launch rockets, which is very expensive. And they were making incredible inroads, but all of a sudden it's ground to a halt because, money.
They've run out of money, that's right. And yes, the reason why I picked this story to cover today is that I've been following this for 30 years. The story.
Oh, yeah.
This company, Reaction Engines, in the United Kingdom, had the vision back in the 90s of building a space plane, which at that time was called HOTOL. And HOTOL's an acronym for Horizontal Takeoff and Landing. And that tells you basically what you need to know about this thing. It flew like a plane, took off from a normal runway, no need for a spaceport, climbed with its two very highly specialized engines to, the region of the atmosphere where you're really not getting very much oxygen in through the air intakes, and then clicked over to liquid oxygen. So it became a rocket motor. And from then straight up into orbit. That vision of that spacecraft is got a different name now. It's called Skylon. But it's the same sort of idea. It's a long, narrow spacecraft with very stubby wings and a couple of these extraordinary engines that would be powering it up into space. And when you look at a diagram, or a cutaway model of one of Reaction Engines' products, and they were still under development, sadly. What you've got is something. It looks a little bit like the engine pod of a modern Airbus or Boeing jet, with an air intake, and it's a supersonic air intake because it's got a very pointy nose at one end, but at the other, instead of a sort of large diameter exhaust, there are rocket motors. And that's what differentiates it. In fact, I think in the final version that they were working on, there was just one rocket motor. And so what happens is when it takes off, it's basically a standard gas turbine, but the air that's coming in through the air intake at the beginning is compressed. It's not liquefied, but it's compressed and then injected with liquid hydrogen, which is the fuel, into one of these rocket motor nozzles and provides a rocket thrust. And as the craft increases its speed, then the ram effect comes into play because it's turning into a ramjet. So a lot of the compression is basically taking place at the front end of the engine. But then when it reaches that height above the atmosphere, and you're talking probably in the region of 30 kilometers, something like that, it cuts out the intake and it becomes a straightforward rocket motor because you then feed liquid oxygen into it. But it's the same motor. It's got two different modes of operating, one in the atmosphere and one not, providing the thrust. Now, as I understand it, I'm not an aerospace engineer, as you know, but the really interesting bit of this and what took reaction engines, I think, from just being a kind of vague notion really into the realm of reality was a heat exchanger. Because when you're going at supersonic speeds, I think it's designed to go up to Mach 5 or something while it's air breathing, 5 times the speed of sound. The incoming air is compressed to a very high degree and has a very high temperature. And you and I know, have talked about this thing before. So they had this heat exchanger that reduced the temperature from 1,000 degrees to sort of -5 or something in 1,000th of a second. It's totally ridiculous. But they made that work. And in fact, it's had other applications, other industrial applications as well. So that's reaction engines have, had contracts to do that. They've been underwritten by the British government. I think they've been underwritten by Rolls-Royce and other companies. Sadly, their funding has just basically run out and the engine is still under development. It still shows promise, Andrew. It's one of these things that as you said, it's a tragic story. And I should say, the engine is called Sabre, and that's an acronym for Synergetic Air-Breathing Rocket Engine. It's a very nice acronym, and it tells you exactly what it is.
Yeah, I hope it's saved. I hope someone like Elon Musk or Jeff Bezos comes to the fore. I mean, they've got money to burn. If you can send a Tesla vehicle to Mars or wherever, surely you can bankroll something that's probably going to change the game completely in terms of getting into space, getting into orbit from the planet's surface at such a low cost in comparison. I mean, I think what I read the other day was that the cost per kilo to send something into space now is about $2,000.
It is.
This could make a huge difference, and it's so sad that they've run into that brick wall because they were onto something.
Definitely, yeah.
Mm.
The other aspect of it. Sorry, go on. Go ahead.
I was just going to say, for people who wonder what it looks like, they've never actually produced one yet, have they? They've just been developing the motor. Is that right?
That's correct.
Yeah,
yes, that's correct.
But the artist's impression, what it looks like, is I suppose there was a plane back in the 1960s built by Lockheed. It was called the Blackbird, and it looks a lot like the Blackbird, which was quite an astounding aircraft for its time. I think I've got the statistics somewhere of the Lockheed, but it could achieve multiple speeds of sound capability, as many aircraft have. But that's I think the closest I can come to what it looks like is a Lockheed Blackbird. Quite an amazing aircraft. You're going to say something, sorry.
Just that, you're absolutely right. SpaceX have brought the cost per kilogram down from about $20,000 to $2,000. This would have brought it down further, but more especially, I think, is that it's highly environmentally friendly because the exhaust was just water. You're burning liquid hydrogen and oxygen. So basically, it's water that's coming out. Now, yes, water vapor is a greenhouse gas, but it's not anything like as bad as some of the things that come out the back end of some other rockets that we know about.
Yeah, absolutely. Another interesting thing, Fred, by the by, I did a little bit of research on some of these high-speed aircraft of the past. The X-15, which was a NASA creation, it came about in the 1960s as well, I think. The X-15s were built operated between 1959 and 1968. There were 12 pilots, including Neil Armstrong, who flew the X-15, and it was the first land-based horizontal takeoff aircraft to achieve space wings, because it could reach a height of 100 kilometers, 67 miles, in fact. And it had a top speed of 4,520 miles an hour, or Mach 6.7. Yeah. So it has been done in the past. In fact, in the very early days of rocket science, the North American X-15 achieved technical spaceflight by reaching what we consider the limit between Earth and space, the 100-kilometer limit. So it's been done before, and they were building on something that would have changed everything. And let's hope that there's been nearly 200 jobs lost as a consequence of this situation. It's really sad. And
you can imagine they were very highly qualified people as well.
Indeed. And hopefully someone will come to the fore and carry on this incredible work, because I think it's vital for the future, especially given, not so long ago we were talking about the pollution that's getting into the atmosphere from multiple rocket launches to put up those satellite arrays. This would be an incredible development if they can just finish the job. Yeah. Anyway, you can read all about it at universetoday.com. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
3, 2, 1.
Space Nuts.
Now, Fred, speaking of orbital satellites, I'm laughing because I love this story for a couple of reasons. This is a story about a satellite that the UK owns and is still responsible for. It went up in 1969. It's still up there, surprisingly, but something weird happened. What the heck is going on?
It has a name. You're going to probably say something about this. Let's do the name first, Andrew. Go on, you cover that. Tell everybody what it's called.
It's called Skynet. If you listen to our sister podcast with my brother Steve, Astronomy Daily, he often talks to Hallie about her uncle Skynet. And Skynet was the self-aware evil entity that was created through online systems in the Terminator movie series, and basically, saw the near end of humankind because it developed self-awareness. So, Skynet. I didn't know there was a real one, but there is.
It is, and as you said, it was launched, I think, in November 1969. Was when Skynet 1A. There were two, apparently, there were two of the first series. I think Skynet actually still exists as a series of spacecraft. But Skynet 1A, it's a geostationary satellite. That means it's at 36,000 kilometers above the Earth's surface, and always hovers above a particular point on the Earth, because the orbital period, the length of time it takes to go around once is 24 hours. Always a very neat trick to be able to do that. So when it was launched, what was it launched for? It was all about communications for the British forces. It was a defence relay communication spacecraft, and it was placed basically over the east coast of Africa. That was where its original location, at 40 degrees east. And of course, what that meant was that because it's on the equator and at 40 degrees east, it can see both the RAF base in the south of England, where it was being controlled from, and various British forces deployments throughout the Asia Pacific. Well, not the Asia Pacific, but certainly Indian Ocean and East Asia. So all of that was part of its original function. Now, that spacecraft, I don't think it actually worked for very long. It was just a few years, and of course that was in the infancy of this kind of telecommunications. And so I think everybody lost interest, Andrew, until recently when somebody said, well, where's that Skynet 1A gone? It turns up basically somewhere else, half a planet away, as the BBC reported. Actually, there's a very nice article on the BBC website for this. It's entitled "Somebody Moved UK's Oldest Satellite and No One Knows Who or Why." That tells you the story. But they comment that orbital mechanics, and that's the way that the dynamics of orbits work. It's what I did my master's degree on. It means it's unlikely that the half-ton military spacecraft simply drifted to its current location. Almost certainly, says the BBC, it was commanded to fire its thrusters in the mid-1970s to take it westwards. It's now over America. That's the thing. And the question is, who was that and with what authority and purpose? The BBC comments, it's intriguing that key information about a once vital national security asset can just evaporate. But fascination aside, you might reasonably also ask why it still matters. After all, we're talking about some discarded space junk from 50 years ago. And the bottom line, there's a space consultant by the name of Dr. Stuart Eaves who comments that it's still relevant because whoever did move Skynet 1A did us a few favours. It's now in what we call a gravity well at 105 degrees west longitude, wandering backwards and forwards like a marble at the bottom of a bowl. And unfortunately, this brings it closer to other satellite traffic on a regular basis. Because it's dead, the risk is it might bump into something, and because it's our satellite, we're still responsible for it. That's Dr. Stuart Eve, space consultant.
That's the bottom line, isn't it? It is these days the responsibility of the country that sends it aloft to deal with it, and they can't because it's a dead satellite. It's stuck in this gravity well. It's bouncing around, and it's it's in a traffic zone basically.
Yes, that's right. Yeah. So the normal thing with defunct geostationary satellites is they're pushed outwards into what's called a graveyard orbit. Yeah, where they are well away from all the active ones and sort of well away from other graveyard orbit spacecraft. So they're pushed outwards, and that's the standard practice and has been for some time. But clearly Skynet 1A hasn't had that. It's in this gravity well, and it probably doesn't have any means of moving it because it's probably out of fuel, and 50 years old. It's more than 50 years old. It's probably a little bit rusty here and there in terms of its electronics and things of that sort.
Yeah. Didn't they expect it to just plunge back down to Earth? Wasn't that the original expectation?
No, geostationary is too far away. Okay. It's 36,000 kilometers. And I guess when that was launched back in 1969, there really wasn't the concern with space debris that there is now. And there would only be... So the way geostationary orbits work, Andrew, there's that they're all at the same distance. They've got to be at the same height above Earth for them to go around once in 24 hours. Otherwise, it doesn't work. So what you've got is the orbit, and it's all on the equator, so it's a single orbit. It's partitioned into stations for the different spacecraft, and I don't think they're very big. I think they're only 100 kilometers or something like that. Each box that one of these spacecraft sits in. One of our friends, Marnie's and my friends, actually she drives these spacecraft. She's a satellite manager for Optus, the telecommunications company here in Australia, and she talked to me. It's a long time ago now, but she talked about station keeping, and it means the gravitational pull of the moon and the sun and the planets just tweak the orbit slightly, and you've got to keep bringing it back to where you want it to be. So there's always a fuel usage with these geostationary satellites, even though they're in what seem like stable orbits. You've got to work to keep them there. And eventually that's why you need to get them out into a graveyard orbit, because if the spacecraft runs out of fuel and you can't do any station keeping, then you do risk it wandering out of its box, its imaginary box, and hitting another one.
Yeah. You mentioned your friend who works for Optus, who tweaks the satellites' orbits to keep them where they need to be. This article you mentioned, the BBC article, spoke to Graham Davidson, who was the original pilot, if you like, of Skynet 1A in the early 70s. He worked for the RAF. He said the Americans originally controlled the satellite's orbit and they tested the software, but eventually handed over control to the RAF. This fellow's now in his 80s. He said, in essence, there was dual control, but when or why Skynet 1A might have been handed back to the Americans, which seems likely, I'm afraid I can't remember. Because it's such a long time, isn't it? Such a long time, and so much has happened over those decades, and here we are suddenly thinking, oh, hang on a minute, it's still there. It's doing the wrong thing. We can't do anything about it. My theory, Fred, is that somebody at Mission Control saw a pretty girl, sat down on the panel with his cup of coffee and said, "G'day, I'm Fred," and pushed a button. That's what I reckon's happened.
It could be. Well, we might find out, actually, because there's a PhD student at University College London by the name of Rachel Hill, soon, hopefully, to be Dr. Rachel Hill, if she does a PhD. And she's been working through the National Archives. And there's a speculation from Rachel, which is a Skynet team from Oakhanger, that's the RAF station, would go to the US Air Force satellite facility in Sunnyvale, colloquially known as the Blue Cube, and operate the Skynet during Oak-out. That this is when control was temporarily transferred to the US while Oakhanger was down for essential maintenance. Perhaps the move could have happened then. And maybe your theory is as good as hers in that regard.
I can see a Bond film in this. The self-aware UK Skynet satellite, and MI6 is thrust into action to deal with it because it's up there plotting the takeover of the world. Well, I think that story's already been done. But anyway, It is amusing. It is amusing, although it does have some serious consequences if it gets in the way of satellite traffic. You can read that at bbc.com. This is Space Nuts with Andrew Dunkley and Fred Watson.
3, 2, 1.
Space Nuts.
Finally, Fred, we look at citizen science, and it's come to the fore in Japan, because this year's been quite an astounding year in terms of being able to observe Aurorae. And the sun's been so very active, and the Aurorae have been popping up in places where you wouldn't normally see them, including where I am, although I haven't been that lucky. But the thing with the ones that have been seen in Japan is that they have been a magenta colour, and people have gone, wait a minute, that doesn't look right. How is it so? Citizen science has come up with the answer.
That's correct. It has. And, you know, it is a really nice story as to how we learn things by virtue of people just doing their thing with their cameras and pulling together all their images. So this was something that happened in May this year, in fact, May the 10th, if I remember rightly. There was a very, very active auroral display, which was seen throughout the world, except here in Sydney, because the sky was cloudy. We didn't see any of it, and I was very angry. My daughters in the UK saw it, and I think that most of Britain were treated to marvellous aurorae, as with Japan as well. And so the photographs that come particularly from Japan showed the aurorae being magenta. It's a sort of purplish colour, like a pinkish purple. And normally what we find with the aurora is the colours are quite specific, Andrew, because they are the colours that are generated by excited atoms in the upper atmosphere. and I'll be looking at the Aurora again early next year, hopefully, and thinking about these things. What causes the green? The green is the most commonly seen color in the Aurora, and that comes about because it's an emission of oxygen atoms in the upper atmosphere. The oxygen atoms are clouted by the electrons and protons too, coming from the sun. In a burst of solar activity, and when the atoms they get excited to a higher level of energy, when they relax, they emit specific colors, and the green light is the specific color of oxygen at a height of between about 100 and 200 kilometers. When it gets higher than that, if there's a higher level of auroral activity and atoms higher than about 200 kilometers are excited, and these are oxygen atoms that we're talking about, then they emit a red light. They emit a different color because the pressure's different. And so that's why we commonly see aurorae with green undersides and a red higher region, up to usually up to about 500 kilometers or so. And that's why here in Australia, we tend to see red aurorae, because people are down in Tasmania and places like that. They're looking over the southern horizon. All they're seeing is the highest levels of aurorae that are happening well below their horizon. That's why we see the red. But that doesn't explain magenta. And that involves something else that comes into play with very energetic aurorae. And we've seen this actually up in far northern Norway. If you've got lots of highly energetic electrons, they also, as well as exciting the green and the red, they penetrate lower into the atmosphere. And then the principal, it's actually a molecule that comes into play, is nitrogen. The nitrogen molecule is then excited to radiate in a range of colors, but they include blue. And in fact, sometimes there's so many of these colors come together that you see a white underside on the Aurora. That tells you there's really highly energetic electrons coming in. And we've seen that, this sort of whiteness on the bottom layer of the Aurora. That's caused by several different excitations, if I can put it that way, of nitrogen molecules. But one of the main ones is blue. And so what the conjecture is here in Japan, and this is where the citizen science comes in, all these photographic observations tell you that the magenta color, knowing where the photographs were taken and what direction they were taken in and how high above the horizon these colors appear, they tell you that the magenta aurorae are at a height of round about 1,000 kilometers. And that is a very high level. So this is because we've got this so much excitation. And what they're suggesting, so yes, at 1,000 kilometers, you'd get red from the oxygen. But the fact that this occurred in May brings the weather into play as well. And it means that the atmosphere was in a sort of what they call a preheated state, which means you get this molecular nitrogen, which is normally emitting at a very low level in the atmosphere, below about 100 kilometers. It bubbles up into the upper atmosphere. And that, when the electrons hit it, gives a blue light. And so what you've got at 1,000 kilometers is a mixture of molecular nitrogen. It's actually ionized. It's lost an electron. And the oxygen. So molecular nitrogen's giving a blue light. The oxygen's giving a red light. And what you get is purple, or this magenta. And this, basically, there were 775 citizen science observations, which were combined with satellite observations in research done by one of the Japanese science institutions. It's a very nice piece of work, and it's lovely that it involves folk in the street like you and me.
Yeah, and so it's as simple as being where they were, what was happening in the atmosphere, and the mix of colours from that point of view.
That's right. Due partly to the time of year, as well as the highly energetic electrons coming in. Yeah, very nice story.
Yeah, well, it's interesting because a lot of the photographs of Aurorae that were taken from my part of the world, around Dubbo in central New South Wales earlier this year, had multiple colours. Like we had greens, we had purples, we had reds, and even some blues. So all of that was happening here as well. So there were a brilliant mix of colours in our part of the world, and I'm so disappointed that I missed that because it looks spectacular, truly spectacular.
Yeah,
maybe a similar effect, Fred, to what they witnessed.
It could be. Yes, it's probably right, Andrew. You were probably seeing similar phenomena. That's right. Multiple colours. By you, I mean you in a sort of general sense.
Not South Wales people.
Yeah, that's right. Although you saw them on the photograph, so that's fair enough. But yes, I think these will be related issues.
Indeed. All right. It's a great story. You can read all about it at phys.org. That brings us to the end of this particular program. Thanks for your company. Don't forget to visit our website if you're trailing around on the internet. It's spacenutspodcast.com or spacenuts.io. Lots to see and do there. You can sign up for the newsletter, Astronomy Daily Newsfeed. You can go to the shop. You can hit the supporter button if you feel so inclined. Plenty happening on our website. Spacenuts.io is probably the easiest one to remember. We're all done. Fred, thank you very much.
It's a pleasure, Andrew. Always great to talk, and I look forward to next time.
Yeah, it could be minutes away. You never know. Thanks, Fred. See you soon. And I would say thanks to Hugh in the studio, but we changed the recording time at the last minute and didn't tell him. And from me, Andrew Dunkley, thanks for your company. We'll see you soon. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.